Good morning, everybody. Let's get started. So, who remembers what did we start in the previous class? Routh Hurwitz tables. And what is the idea behind Routh Hurwitz tables?
Figuring out the right-hand poles.
How many poles are in the right-hand side? And the idea is that it is easier to know the number of poles that are in the right-hand side, or roots, than to find the actual roots. Together? So then we said, in order to establish the Routh Hurwitz table, if we have a polynomial, we have to calculate the entries. The first two rows of the polynomial come directly, the first two rows in the table come directly from the polynomial. And then we have to calculate the rest of the entries in the table. And if you take any entry, that entry is taken by -1 over the first element in the row above it, multiplied by the determinant established by the two rows that are above, an minus 1, an minus 2, an minus 3. This column stays throughout all the calculation of that row, and an minus 1. And then we alternate, we choose this column to calculate the relative entries. Okay, so that is hopefully straightforward. And then we've done an example. We calculated the Routh Hurwitz table for this polynomial. Again, 1 and the coefficients of the odd, which is 1 and 2, and then the even, 1 and 8. And then we calculated this entry, which is the -1 over this one, multiplied by the determinant of 1 and 2 and 8. And that will give me a -6. We do the same thing here, -1 over 1 and 0, so therefore it's going to be a 0. And then the 8 is the -1 over the -6, 1 multiplied by 6 minus 6 multiplied by 8, which is going to be an 8, which is right there. Make sense? Everybody can do this calculation? Okay. So let's do another example, and then we'll see what we're going to do with this Routh Hurwitz table. So let's say we have a polynomial, P of S, that is equal to 1 s to the 6 plus 4 s to the 5 plus 3 s to the 4 plus 2 s cubed plus s squared plus 4 multiplied by s plus 4. What do we do? We're going to write s to the 6, s to the 5, s to the 4, s to the 3, s to the 2, s to the 1, s to the 0. And what goes in the first row? 1, 3, 1, and 4. What goes in the second row? 4. No, I am. 4. What is the second entry? 2. And the last one is 4. Together? I see the look on everybody's face. So the second row is 4, 2, 4. Why did I not write it here? Because we can always take any row and divide it by any constant. Does it make sense? So I can write this as 4, 2, 4. So that should be fine. 4, 2, 4. Or I can say, oh, these all divide by 2. So why don't I just write it as 2, 1, 2. Make sense? It just makes the calculations easier. I mean, just the number gets smaller. Is that clear, everybody? So this is original row, And then what we're going to do is we're going to divide by 2, and then we're going to put the entry here. Okay, can I have you calculate first the row, after that, the s to the 4? Anybody needs a pencil?
What's the second purple?
Hurwitz.
Hurwitz.
Hurwitz. Anybody calculated the first entry? No.
Then I've done the whole table.
But I mean, it has a 5 in the answer. What is it? 5 over 2? Yes, 5 over 2. So it's going to be a negative 1 over 2, the determinant of 1, 3, 2, and 1. It's going to be 1 minus 6 multiplied by negative 1 over 2. What is the second entry?
I'm sorry, where did the negative 1 half come from?
Negative 1 comes from the expression
Okay.
divided by the first entry here.
Okay, that's what I didn't do.
1, this happens to be a 1, so we had a 1. But in general, negative 1 over an minus 1. Any second entry? No. This element here. Negative 1 over 2, 1 times 2 minus 1 times 2. What is it going to be? 0. Is that clear, everybody? What is the third element going to be? We can add a 0 here. Anybody? It is a 4. Negative 1 over 2, and then 1, 2, 4, and 0. 1, 2, 4, and 0. And apparently, every time this element is above a 0, it's just going to come down as is. The result is going to be such that it is a 4. Okay, what do we do next? We're going to calculate the row that is below it. What is the first element in the row below it?
1.
It's a 1. Excellent. It's going to be negative 1 over 5 over 2, and the determinant of 2, 5 over 2, and 1, and a 0. Again, it's above a 0, so it's just going to fall down as is 1. What is the element after that? So this element is going to be negative 1 over 5 over 2, and the determinant of the 2 and 5 over 2 and 2 and 4. So therefore, it's going to equal to negative 6 over 5. Okay. And then we don't have any entry, so it's a 0. So we continue doing the same calculations. We're going to get a 3 here, and then we're going to have a 4 here. Continuing the row below it is going to be negative 38 divided by 15 and a 0. And continuing, we're going to get a 4. Together? Okay, so what do we do with this table? What the Routh Hurwitz says is that the number of roots in the right half plane is equal to the number of sign changes in the first column that we calculated here. So the Routh Hurwitz criteria. It's equal to the number of sign changes in the first column of the Routh Hurwitz table. What does that mean? If I look at this table, how many sign changes I have in the first column? 1? 2. 2. We have a change from positive to negative, then from negative to a positive. How many sign changes we have? 2. So therefore, we have 2 roots that are in the right half plane. Is that clear? Makes sense? So if this was the characteristic equation of a closed loop system, is this system stable? Unstable. We have roots in the right half plane. Okay. So therefore, if I want to check for the system to be stable, What should all the first column signs be?
All positive or all negative?
They should be all positive. I mean, if they're all negative, we can just take the negative sign. They're going to become all positive.
Right.
All elements in first column must be positive. Together? Straightforward? Okay. Is that clear, everybody? Okay, what could go wrong with this method?
Miscalculation.
Miscalculation. What else? What could go wrong that we have to address? Miscalculation. It's calculated correctly. Can anybody think of what could go wrong?
Missing an S to the power of something that isn't there.
Well, if it's missing an S, then the system is unstable anyway.
Oh,
But when you do the calculation, go ahead.
If you get a 0 in the first column?
Excellent. Excellent. What happens if we get a 0 in the first column? Why is that a problem? Because we're going to be calculating, we're going to be dividing by that 0, and if it's a 0, we're not going to be able to continue. Is that clear? So therefore, what we're going to be doing next is we're going to look at the special cases we might encounter when we're calculating the Routh Hurwitz table. So the first special case is what happens if one of the elements in the first column is a 0. So as an example, we have a polynomial p of s, s to the 5, plus 2, s to the 4, plus 2, s cubed, plus 4, s squared, plus 11s, plus 10. S to the 5, s to the 4, s cubed, s squared, s to the 1, s to the 0. And this is 1, 2, 11. And this is 1, 2, and 5. And if I calculate the first column here, the first entry here, it's going to be 1 times 2 minus 2 times 1, which is going to be a 0. Second entry we can calculate. Now if I come to calculate the entry here, I'm going to have a problem because I need to take negative 1 divided by 0. Together? Everybody? And you see here I divided by 2. So I had 2, 4, and 10. Okay, so let's see what we do if we have a first entry in the row that is a 0. Apparently, we cannot proceed since we will be dividing by a 0. However, we might want to proceed to know the number of roots that are in the right half plane. We have two methods. So let's see how we proceed when we have a row that is the first entry that is a 0. Okay. So I'm going to draw a line, and we're going to introduce each one in one side of this table. So the first method is we're going to replace the 0 with a very small number. What are we going to call this small number? We're going to call it epsilon. And then we're going to continue the calculation. And then we're going to see what happens when epsilon goes to 0. Together? So let's look at the example we've done. We had s to the 5, s to the 4, s to the cube, s to the 2, s to the 1, s to the 0. And this was a 1, a 2, and 11. This was 1, 2, and 5. So the first entry is a 0. I'm going to replace it with epsilon. The second entry is a 6, and the third entry is a 0. So I'm going to proceed with this epsilon. So I'm going to calculate the next entry, which is here, is going to be negative 1 over epsilon, and then 1 multiplied by 6 minus 2 multiplied by epsilon. And therefore is going to equal to 2 epsilon minus 6 divided by 2. By epsilon, sorry. Together? Calculate this entry from these two rows. 1 epsilon, 2 and 6. 1 times 6 minus 2 times epsilon. 1 times 6 minus 2 times epsilon. The next element is going to equal to a 5. Since I have a 0 here, this is just going to come down. What do we do next? We continue. So we're going to calculate the next entry. And this entry is going to equal to negative 1 over 2 epsilon minus 6 divided by epsilon. And then 5 times epsilon, or epsilon times 5 minus 6 times 2 epsilon minus 6 divided by epsilon. Make sense, everybody? Negative 1 over this minus this. Okay, so if we simplify this one, we're going to get negative 36 plus 12 epsilon minus 5 epsilon squared divided by negative 6 plus 2 multiplied by epsilon. And then we have a 0 here, and then the 5 will come down here. Is that clear, everybody? Okay. So what we're going to do next is we're going to see what happens when epsilon goes to 0. So when epsilon goes to 0, we're going to see when it approaches a 0 from the right, when it approaches epsilon from the left. So I'm going to take epsilon, that is equal to 0.01, And I'm going to calculate when epsilon is equal to negative 0.01. So I'm going to go back to my first column, and I'm going to substitute for epsilon. And if I do that, I'm going to get, in the first column, I'm going to get a 1, and then the epsilon, which is 0.01. And then I'm going to substitute for epsilon here. What is, if I substitute epsilon, what is this going to equal to? Approximately negative 6 over 0.01. Because the epsilon is very small, so I can ignore it. Negative 6 over epsilon, negative 6 over 0.01. And then if I substitute for epsilon in this expression, what is this expression going to equal to? Give it your best shot.
6.
Excellent. It's going to equal to a 6. Because this is going to be very small compared to 36. This is very small compared to 36. So I just have negative 36. This is going to be very small, negative to 6. So this is approximately equal negative 36 over negative 6, which is a 6. And then I have a 5. Okay. So therefore, if I look at this, how many sign changes we have? 2. We have a sign change, and then we have another sign change. Okay, so we're going to do the same thing, but now when epsilon is equal to negative 0.01. So if we do that, we're going to get a 1, we're going to get a 1, and we're going to get negative 0.01, we're going to get 6 over 0.01, is that clear? So same thing, epsilon is very small, it's going to be negative 6 over epsilon, but epsilon is negative, so it's going to be 6 over 0.01 instead of negative 6 over 0.01. And then we're going to have a 6, this is not going to be impacted by epsilon, and then we're going to have a 5. Together? How many sign changes we have? 2. And therefore, since we have 2 sign changes, whether we're approaching epsilon from the right or left, we conclude there are 2 sign changes, and therefore there are 2 roots that are in the right half plane. Together?
Will it always have the same number of side changes on both sides?
Of course not. If it was the same, then why would I have calculated it?
Right.
I would not. So now I'm going to leave you curious. What happens if they're not the same? We'll look at an example when it is not the same. I mean, they asked what happens if we do not have the same sign changes, whether we're approaching epsilon from the right or left. And we'll do an example, we'll illustrate what happens. So for the time being, we're replacing with epsilon, we're continuing, and we'll see how many sign changes. So this is the first method. Just look at the second method. And the second method, what we're going to do is we're going to change variable. So instead of having the polynomial expressed as in terms of s, we're going to express it in terms of x that is equal to 1 over s. Now we know if I have a polynomial q of s equal to 0, if I replace it with the q of 1 over x, is going to equal to q of x divided by x to the n equal to a 0. Or q1. So this means the roots of q of s and q of 1 over x are reciprocal of each other. And therefore stability is not affected. What does that mean? Let's look at a simple example. If I have a polynomial that is s minus 1 multiplied by s plus 2 equal to a 0. What are the roots of this polynomial? 1 and negative 2. Agree? What if I replace s with 1 over x? I'm going to get 1 over x minus 1 multiplied by 1 over x plus 2, which is going to equal to x squared 1 minus x multiplied by 1 plus 2 multiplied by x. And if I set this equal to 0, what are the roots of this polynomial? X equal 1 and x equal to, this is negative 2, negative 1/2. Agree? See it? So if I have a polynomial that has roots at 1 and negative 2, if I replace s with 1 over x, I'm going to get a polynomial that has roots at 1 over the 1 and 1 over the negative 2. How does this help us? Since we are not interested in finding the roots, but finding the location of the roots, whether I find the root or 1 over the root, it does not matter. Because what I'm looking for is the sign of the root. Does that make sense? I'm not trying to find where the roots are. Well, I'm trying to find whether the roots are in the right half plane or not. Make sense? So really the value does not matter to me. What matters to me is the sign of the roots. So therefore, the sign will preserve the location of these roots. Okay, so going back to our polynomial. So to proceed with previous example, the polynomial that we had was s to the 5 plus 2s to the 4, 2s cubed, 4s squared, plus 11s plus 10. So what we're going to do, we're going to calculate the polynomial of p over x, which is going to equal to 1 over x to the 5 plus 2 multiplied by 1 over x to the 4 plus 2 multiplied by 1 over x cubed plus 1 over x, 4 multiplied by 1 over x squared plus 11 over x plus 10. So what we've done on this polynomial, we just we substitute for s with 1 over x. Okay, so if you put the terms together, this is going to equal x to the 5, 1 plus 2x plus 2x squared plus 4x cubed plus 11x to the fourth plus 10 multiplied by x to the 5. Agree, everybody? Okay. So therefore, we can go back to our Routh Hurwitz and create Routh Hurwitz table for the second polynomial, P2, that is equal to 10x to the 5 plus 11x to the 4 plus 4x cubed plus 2x squared plus 2x plus 1. So we're going to have x to the 5, x to the 4, x cubed, x squared, x to the 1, x to the 0. So the first column, the first row is going to be 5, 2, and 1. Where is the 5, 2, and 1 coming from?
10, 4.
Yes, originally this was 10, 4, and 2, and we divided by 2. So just to make the calculation easier. And the second row is going to be 11, and 2, and 1. And then we're going to calculate these entries. We're going to get 12 over 11 and 6 over 11. How can I simplify this row? I can multiply by 11 and divide by 6. So I'm going to do multiply by 11 and divide by 6. This is going to become a 2, and this is going to become a 1. Just to make the calculation easier. Okay, so continuing, we're going to get a negative 7 here. And then we're going to get 9 over 7 here. And we're going to get a 1 here. Okay. How many sign changes we have in the first column? 2. And therefore, 2 sign changes means we have 2 roots in the right half plane. Okay. Let's look at another example. So we can use any of these 2 methods. Using epsilon or replacing s with 1 over x and preceding. Okay, let's look at a polynomial s cubed plus s squared plus 2s plus 2. S cubed, s squared, s to the 1, s to the 0. Okay. First column, first row is going to be 1 and 2. Second row, 1 and 2. What what are we going to be getting here? A 0. What are we going to do? Replace it with epsilon. And then we're going to proceed. What are we going to get here? We're going to get here a 2 because we have a 0 here. Negative 1 over epsilon, 1 times 0, minus 2 times epsilon. This is going to get the 2. Okay. So what happens if epsilon goes to 0 and we're going to take a positive 0.01? How many sign changes we're going to have? No sign changes, yes. What if epsilon goes to 0 and from the left side, so it is negative 0.01. How many sign changes we're going to have? 2. So therefore, when we have a case, when we go epsilon from right, no sign changes, epsilon from the left, 2 sign changes, it means these 2 roots are on the j omega axis. When epsilon is equal to 0, we have 2 roots on the j omega axis. Sounds good? Answer your question there?
Yes.
Okay. What else can go wrong with this method?
Could you have a different amount of sign changes? One not being like 0, and the other one being 2, like we just did? Could be like 3 sign changes, or 4 on one side, 2 on the other.
Potentially you could. And
They both mean the same things.
if you have a different sign changes going from right and going from left, the difference between them is going to be the roots that are on the j omega axis. I mean, try to find an example. We can do it. Okay. So what else can go wrong?
Maybe your entire first column is negative.
No, if the whole column is negative, we can take the negative sign off. That will not affect the roots, isn't it? So if all the entries are negative, it's the same as all the entries are positive. So special case 2, which is if we have all elements in a row are 0. Okay. So let's look at an example, which is the example we just done. S cubed plus s squared plus 2s plus 2. So when we calculated the Routh Hurwitz table, we got a 0 here. Now in this special case, because this is a very low order, we can treat this as epsilon and continue. But if I look here, this whole row is a 0. Make sense? This whole row, this row should have only one entry, and this entry is a 0. So we call this a row of 0. And when we have a row of 0 like this means that the row that is above the row of 0 is a factor of the original polynomial. So what that means, what is the polynomial that is above the row of 0? S squared plus 2, isn't it? This polynomial that is above is s squared plus 2. Everybody confused? So what we're saying, when we have a row of 0, we're going to go to the row above it. We're going to take that polynomial that is established by that row, which is, in this case, this is s squared plus a 2. This s squared plus a 2 is a factor of the original polynomial. So what that means, I can factor this original polynomial as equal to s squared plus 2 multiplied by s plus 1. Together? Everybody? Anybody confused?
Where did the S plus 1 go?
I divided this polynomial by s squared plus 2. I got s plus 1. I mean, what this told me is this is a factor. Then I just have to find the rest. Okay. So when we have a row of 0, this means P of s, the polynomial, contains an even polynomial as a factor. And we're going to refer to this polynomial as the auxiliary polynomial. And this auxiliary polynomial appears in the row above the row of 0. Okay. So what we're saying again, when we have a row of 0, it means the row above it, the polynomial established from the row above it, is a factor of the original polynomial. And in order to continue, we will differentiate the auxiliary polynomial, and we replace the row of 0 with the result of that differentiation. So in this case, the auxiliary polynomial, and I call it P2 of s, was equal to s squared plus 2. So therefore, if I differentiate it, I'm going to get 2 multiplied by s, and therefore I'm going to go to my table, s cubed, s squared, s to the 1, s to the 0. We had a 1, a 2, 1, a 2. And now I'm going to replace the row of 0 with the differentiation of that polynomial. What is that going to be? A 2. So this 2 is coming from this one. And then I'm going to proceed. Since I have a 0 here, I'm going to get a 2. Okay. So if I look here, there are no sign changes. This means there are no roots in the right half plane. If I look here, there are no sign changes. This means we have 2 roots on j omega axis. Anybody not confused? Everybody is confused, isn't it? Here I'm saying there are no sign changes. Oh, okay, there's no roots in the right half plane. Oh, there's no sign changes here. 2 roots on the j omega axis. That's very confusing, isn't it? Okay, so let's clarify why is that case. So when I find the row of 0, this is a factor of the polynomial. How many roots does this one have? S squared plus 2. 2 roots, isn't it? What are these 2 roots going to look like if I have a second order polynomial? They're going to look something like this. They're either going to be a root on the right, a root on the left. What is the other option? 2 roots on the j omega axis. Together? If I have a second order even polynomial like this, I have 2 options. Either the root's going to be equal to, is going to be s squared, for instance, plus 1, or s squared minus 1. If it is s squared minus 1, I'm going to have a root on the left, root on the right. S squared plus 1, 2 roots on the j omega axis. Make sense? So I try to find, for this auxiliary polynomial, there are no sign changes, which tells me that this is not the case. There is no roots on the right half plane. Where are the roots going to be? On the j omega axis. Does that make sense? Go ahead.
Can you just tell by setting the polynomial equal to 0 and then solving for x, or solving for s?
Yeah, but the whole premise of what we're doing, it's easier to do this than to find the roots. The whole idea is we don't want to find the roots. Does that make sense? Now in this case, it's easy to find the roots. But if it was s to the 4 or s to the 8 or s to the 10, it's not going to be easy to find the roots. The whole idea is we don't want to find the roots. We just want to calculate this. Is that concept clear? Everybody? So if we have a second order polynomial, we're going to have roots. Either going to look like this or they're going to look like this. There's no other choice. If I had a sign change here, it means this is the case. I have one on the right, one on the left. No sign changes, it means I have this case. 2 roots that are on the j omega axis. Okay. And the same thing applies if it is a 4th order. What are the options for the roots if it is a 4th order? I can have a root here, a root here, a root here, a root here. I can have a root here, a root here, a root here, a root here. I can have a root here, a root here, a root here, a root here. I can have a root here, a root here, a root here, a root here. Make sense? So if this was, instead of it being a 2nd order, was a 4th order, then I'm going to have one of these cases. If I have one sign change, then I have 2 roots on the j omega axis, one on the left. If I have 2 sign changes, then I have 2 roots on the right, 2 roots on the left. 2 sign changes, 2 right on the right, which is the same as this case. No sign changes, it means these 4 roots are on the j omega axis. Together? Any questions? Okay. Okay, let's do an example. That illustrate this. So what I'm gonna do, I'm gonna divide this into 4 sections so you can look at them all at the same time and compare them. So the first polynomial is s cubed minus s squared plus s minus 1. The second, s cubed plus s squared plus s plus 1. And the third, s cubed plus s squared minus s minus 1. And the fourth, okay, can I have you do them and tell me for each case how many roots are in the right half plane? And some of these will have a row of 0. So you're going to differentiate the row above it.
Is D S cubed minus S squared?
Yes. Thanks. And I'm going to suggest you do your work and then leave it, and then we'll do it together. But so you can go look back and see what you did wrong if you do anything wrong. Which one are you working on? Okay. Can we do it together? You guys making good progress. What's your preference? Okay. Let's do it together. So SC cubed, S squared, S to the 1, S to the 0. We have a 1 and a 1. And we have negative 1 and negative 1. And apparently, when we calculate this row, we're going to get a row of 0. And these two elements are the same. So here we're going to get row of 0. So that tells me that the line above it is a factor. So what is the line above it? What is that factor going to be?
Negative S squared minus 1.
Excellent. Negative S squared minus 1 is a factor of this polynomial. So to proceed, we're going to differentiate it. So the auxiliary polynomial was equal to negative S squared minus 1. I'm going to take the derivative, which is going to equal to negative 2 multiplied by S. I'm going to replace the 0 that originally was here with the negative 2, and I'm going to proceed. I'm going to get a negative 1. Everybody got something similar? Yeah? Okay, everybody should get something similar. Okay. So now I need to interpret this data. If I look here, how many sign changes I have? I have one sign change. What does that mean? It means I have a root in the right-hand side. If I look here, how many sign changes I have? None. Which means, where are the roots going to be?
It's on the right-hand side.
No, if there are no sign changes here, it's going to be on the j omega axis,
Oh, okay.
which is the case. I'm going to have two roots on the j omega axis. Okay. Let's look at the second one, and hopefully when we compare them, it will become more clear what we're talking about. S squared, S to the 1, S to the 0. We have 1, 1, 1, 1. Same thing, I have a row of 0. The polynomial is equal to s squared plus 1. I'm going to differentiate it. A prime is going to equal to 2s. This is going to be a 2, and this is going to be a 1. How many sign changes I have here? None. Which tells me there is no root in the right half plane, which means I have a root here. And for the auxiliary polynomial, how many sign changes? None, which tells me that the roots are on the j omega axis. Together? So here is a case where we have a sign change above the auxiliary polynomial, which told me there is a root on the right hand side. There is no sign change. The root is on the left hand side. Let's look at the case above it. Below it. We have s cubed, s squared, s to the 1, s to the 0, and here we have 1, negative 1, 1, negative 1. I'm going to have a row of 0. What is the polynomial? S squared minus 1. I'm going to differentiate it. It's going to give me 2 multiplied by s, so this is a 2, and this is a negative 1. How many sign changes I have here? None. How many sign changes I have here? 1. So where are the roots? I'm going to have 1 in the right half side and 2 in the left hand side. Does that make sense? So remember, I have s squared as this is a factor of this polynomial. So how many roots are left? 1 root that is above this calculation. That root happens to have no sign changes, which means this root is in the left hand side, and these 2 roots are coming from this auxiliary polynomial. Okay. Okay, the last case, we have s cubed, s squared, s to the 1, s to the 0. We have 1, negative 1, negative 1, and a 1. We're going to have a row of 0. And therefore, the auxiliary polynomial is going to equal negative s squared plus 1. I'm going to differentiate it. A prime is going to equal to negative 2. And therefore, negative 2 is going to come in here, and 1 is going to come in here. Okay. So if I look here, how many sign changes I have here? 1, which means there is a root in the right half plane. And if I look for the auxiliary polynomial, how many sign changes? 1, which means it has a root on the right half side and 1 in the left hand side. Together? Is that clear, everybody? Any questions? Questions? Okay, let's do one more example. So we are given the system below. And we're going to find K such that the system is stable. We have 2 over s cubed plus 4s squared plus 5s plus 2. Okay. So we're going to calculate the closed loop transfer function. Which is going to equal to 2k over s cubed plus 4s squared plus 5s plus 2 plus 2k. How do I know the values of k that will make this system stable? What are we going to do? What are we going to use? What tool are we going to use? Routh Hurwitz. We know if the first column does not have any sign changes, it means the system is going to be stable. So I'm going to have 1, a 5, a 4, and then I'm going to have 2 plus 2k. And then I'm going to calculate. This is going to equal to 18 minus k divided by 4. And then here I'm going to have 2 plus 2 multiplied by k. What do I have to make sure? That there are no sign changes. When will I have a sign change here?
K is larger than 9.
Excellent. So therefore, I want k to be less than 9. When am I going to have a sign change here? When it is less than -1. This is -5, this is going to be negative. So therefore, k between -1 and 9 to ensure the system is stable. Sounds good, everybody? Are you guys doing the homework? And expecting a quiz every Monday? If you're not expecting a quiz, we'll have a quiz.